So hello everyone, and welcome to the I think 11th lecture of the information visualization course. Today I have a treat for you. I have with me Jack van Wijk here, who is going to give us a guest lecture entitled "Visualization for Transparent Decisions." Jack is a professor of visualization at the Eindhoven University of Technology. He has a massive number of publications on his record, and he was recently awarded with the Test of Time award on IEEE VIS 2020, which is the top or the premier conference in our field. And so it's a treat to have him here. It's an honor and a pleasure for me. So this lecture is gonna have a more classical or classic structure. So you will be invited to ask your questions during the breaks and or towards the end. So we're not going to do Discord today. So you're going to have please prepare your questions, and Jack will be happy to answer them. So Jack, thanks for coming, and take it away.
Thank you, Jan. Very much thanks for inviting me. It's a pleasure to give a lecture. And, I have good memories on the projects we were in together. Today, I would like to talk about visualization for transparent decisions. It's about a mix. First, I'll give very shortly my take on InfoVis and visual analytics. Then I'll zoom into the need for transparent models. I'll show you a number of examples during what I show. They're mainly from Eindhoven. Main reason for that is simply that I know these the best and can tell some backstories about it. If you have a question, you can put it on the chat. After roughly 15-20 minutes, I'll have a little break and ask explicitly you for questions. And Jan told me that he is happy to act as a moderator. So, 10 years ago, everybody was talking about big data. 5 years ago, we were talking about data science. Now everybody is talking about AI. There's confusion about this. Most people think that big data is about data, but it's not. It's about people. Yeah, because in the end of the day, it's people that produce the data, collect the data, and also people that want to get insight in that. And of course, we from visualization have a simple answer how to get this insight. Let's make a picture. Okay, done, solved. We rely on the strength of the human visual system. As Jan probably has told you, it's not only the eye, but also a large part of your brain, 30–40% is dedicated to processing the info. You've probably know the Enscombs quartet. Did you already show it, Jan?
Yes.
Good. So you know this picture. You can skip that, very efficient. Okay. The problem here is, of course, that if you go to real world cases, data can be big, and data can also be messy, and well, how to deal with that. The old school approach is, no, there are a lot of standard diagrams if you use Excel, Tableau, Power BI, whatever. You can use them, but you'll also find out that they don't scale in many cases. Especially difficult are networks. They quickly lead to hairballs, and then you really have to do something else to get insight into your data. Some 20 years ago, 30 years ago, we all believed in the power of the human visual system. We worked hard to develop new visual representations. This is an example from our team, from a tool called Sequoia View. Here we show the contents of a hard disk. Each rectangle represents a file. The bigger the file, the bigger the rectangle. The color indicates the type of the file. And one addition from us was the that we brought in shading to make the hierarchical structure better visible. Well, We made this available as a downloadable tool and got a lot of nice reactions. People said this really saved me from buying a new hard disk. Other people reacted with, I have no idea what the pictures mean, but they look pretty cool. Also nice. If you think this is somewhat extreme, you can make it much weirder. This was the work of a master student. My colleague Huub van der Wetering had at some point an idea, okay, we are talking about hierarchical structures, about trees. Well, let's get inspiration from the real world and try to map an abstract tree to a botanical tree. And our student worked hard on it. The visual encoding is that the stem of the tree, the root, is the main folder. The sub-branch is a subfolder. And most important discovery of this project was that it's a bad idea to use leaves as a metaphor. You should use fruit. You see those funny spheres? That denotes a collection of files. Each little cone on a sphere denotes one particular file, and again, the bigger the cone, bigger the file, the bigger the sphere, the larger the collection. We used a lot of algorithms from botanical visualization, very clean, very cool algorithms. For instance, to put all the cones on the sphere, and by playing around with the parameters and looking at your hierarchy from all sides, you could be very fascinated. Okay, this is old school, right? We try to go to the extreme in visual representation, use 3D, lots of colors, etc., etc. But gradually, we, myself, and also our community discovered that there are boundaries that you hit. Here's a simple example. Pie chart, very popular still, unfortunately. Now look at the pies and try to sort these for increasing size. That will take you some time. The problem here is that we are not very good at perceiving angles. Yeah, we can clearly distinguish if something more or less than 45 degrees, no, 90 degrees or 180 degrees, but for instance, the gray and the yellow, you have to look very carefully. Now, let's have a look at the other visual representation of the same data. Well, here it's immediately obvious what the pattern is. We rely on looking at positions, and that's much more effective. So that's an overall pattern. You see in our community that people are going back more and more to simple representations, standard workhorses of day-to-day business graphics. Okay, so far for presentation. Another route, of course, is interaction. Some examples of that. This work from a master student again, visualizing data from MRI scanners of Philips. Philips is doing maintenance for these, and there's a collection of thousands of those MRI scanners. In the first box, you see a list of these with attributes. You can select one of those. On box number 2, you see a calendar that shows events over the year. You can select, of course, yourself what events you are interested in and how you want to highlight these. In panel 3, you see one particular day, probably zoomed in to just a couple of hours, and then you see a pattern of events. And then finally, you can click on an event, and in box number 4, you see all the hairy details of the event. Well, this is typically Schneiderman's mantra in action. Overview first, zoom in and filter, and then finally the details on demand. typical pattern here is that we try to stick to one screen showing multiple views, no pop-ups, no multiple tabs, and try to keep everything as stable as possible. Another master project. This was work for the Dutch Institute on Health, RIVM. They collect data about resistance against antibiotics. The data set here was 650,000 tests done. And for each test, they checked out, okay, what is the resistance pattern? Of course, that's a lot. Students worked hard to visualize all this. On the left, you see the most occurring patterns. In the middle, you can select specific patterns. Nasty detail here was also that those tests not always went right, so there was missing data that had to be imputed, and the column on the right shows more information about that. It's work of Stefan Else, at that time PhD student, since February 1st back in our group as assistant professor. Suppose that you have a large network. Well, it's very difficult to visualize, but in many cases you're just interested in a subset. Here the data set is migration among counties in the US. So very dense network, and each node, each county, but also each edge has a number of attributes. On the left, there are a number of centered widgets that you can use to select what you want to see, both for the edges and for the nodes. You can make a selection in your visualization, denoted by the colored boxes. And on the right, you see a sort of simplified view that shows a summary of the information contained in the box. Well, the pitch we made here was that on one hand, you want to see all the details and be able to drill down and make your decisions yourself. In the end of the day, you also want to have a summary that you can present to other people and transfer the knowledge that you obtained. One of the recommendations I make to my students all the time is try to steal wherever possible. Don't try to reinvent the wheel. If you have some common problem, reuse existing metaphors. Well, the centered widgets shown on the left are one example, but also, yeah, we were dealing here with multiple selections of the data, and for that we stole metaphors from Photoshop. Yeah, you can enable and disable them by clicking on an eye. You can sort them to deal with priority. You can edit them, etc., etc. Okay, so far for interaction. Interaction, many cases, is crucial to get insights fast. But if data gets larger and larger, you have to throw in more heavy machinery from statistics, machine learning, data mining. I understood from Jan that he already told you about visual analytics. Well, the idea, of course, is pretty simple. You have data, you have some model, and you present the results of the model to the people, and you visualize that. And the strongest pattern is when you can show both the data, the raw data, as well as the outcome of the model. In some sense, there's totally nothing new here. We've seen that before. Here you see exactly this pattern. You have the raw data shown in the scatter plot, but also you see the result of the model. In this case, very simple linear regression model. Now, the big challenge for me and also the community is still, okay, what if things scale up? What if you have thousands, maybe millions of points? What if you have tens or hundreds of thousands of dimensions? Yeah, we're still struggling to make tools that are as simple and clear and effective as this. nice little scatter plot. Of course, interaction also plays a role here. And in this case, not only for the visualization, but also in interacting with the model. In the ideal case, hoping that everything is fast enough, you can steer your model towards something that makes sense and is effective. Okay, this is what visual analytics leans on. Computers are very, very good at doing very simple things very fast. Humans, on the other hand, well, they know about the domain, they're flexible, and literally they can see things that are very hard to compute. I must admit that this is a bit a rosy picture. I collaborate now and then with colleagues who know much more about psychology, and they always tell me, well, why do you want to have this human in the loop? Yeah, don't you know that there's a lot of problems in bias and limitations, etc., etc. And well, in many cases, yeah, I see that point and have to agree. By the way, the word human in the loop, Ben Schneiderman is one of the heroes in our field, and he explodes when people talk about human in the loop. He says it should be machine in the loop. Yeah, the human should always be in control. If you want to read more thoughtful things, then check out what Ben Schneiderman has written in the past years. Okay, here is my simple picture of the field, and I think it syncs with something John and I just discussed before the lecture. It's sort of continuum. Yeah, if things are simple, use business graphics. Nothing wrong with using Excel, Tableau, etc. If things are a bit bigger, then you have to throw in methods from InfoVis. And if things become really difficult, then it's often a good idea to use a visual analytics approach. In all this, yeah, it's a bit strange, but in many cases, the main job is not to show all the data. The important job is also to get rid of the data. Yeah, try to simplify, to try to aggregate, zoom into only the things that you want to know. Each time when I have someone coming to me and asking for visualization, the very first thing I do is trying to convince them to use Excel to solve their problem. Yeah, okay. And if it can be solved by Excel, great. And then no need to think about it or define a student project. Things are getting interesting, of course, when it's not that easy to do it with just Excel. Of course, when you try to get rid of data, there's a big chance that you might miss something. And that's why we still like to use visualization. I'll show some examples of visual analytics. This is already a very old picture I made before joining TU Eindhoven. It shows work I did at ECN, the Energy Research Institute. In this case, it shows the energy consumption of the institute over the year, so-called fingerprint plot. On one axis you have the days, on the other axis you have the hours of the day. The value is encoded in this case by height and by color. Well, this is a typical visualization approach, trying to show a lot of data in parallel. This image was a bit a shock for the people that looked at it. Not because of the subtle patterns that you see, like in summer less energy is used than in the winter, but especially because of the big block that's on the bottom. Yeah, 24/7, 365 days per year. the base load is quite high. The explanation was that probably a lot of big experiments are going on that have to run continuously. Okay, this typical visualization solution. It has its limitations though. If you want to know, for instance, if Mondays are different from Fridays, then this picture doesn't answer that. So I tried to go for something very different. The data I show here is other data. In this case, I must admit it's very clean data, so that helps to get the story across. The data I show here are the number of people that are present at the institute. I had access to all the data for everybody that was clocking in with their card. That time we didn't have issues with privacy or GDPR. Those were the days. I aggregated these data and counted, okay, given a certain moment in time, how many people are there. Next, I was hunting for typical patterns over the day. And I applied clustering. Yeah, day patterns that were similar were put in the same cluster. And here you see a visualization. On the right, you see the day patterns. On the left, you see their distribution over the year. Now you can see that there is dark orange, light brown color on top. Can you see my cursor?
Yes.
Okay. Here, this one on top represents standard average working days, like here. Here we see a dark brown cluster that represents Fridays and also days in the summer. There's a green cluster here. That's a mix of those Fridays in the summer. There are blue days, like for instance, day after New Year's Day, this day after Ascension Day. This is Animal Day, but that was not the reason that people worked at Saturday. It was an open day of the institute and people clocked in to host the visitors. Of course, there are weekend days, the flat line shown over here. My all-time favorite cluster is represented here with a red line. Well, I guess looking at the audience, most of you are Dutch, and we'll see immediately the explanation. This is Santa Claus, and everybody is allowed to go home to the family to celebrate Santa Claus at home. And the shift in the red curve. Okay, I didn't explain you the visualization, right? On the left, you see a funny matrix with some sort of irregular patterns and some labeling known as a calendar. Of course, you know a calendar, proven technology, you know how it works, very effective, shows the cycles, shows a nice subdivision in months, quartiles, etc. Very powerful. Ideal if you want to show distributions over the year. On the right, you see some funny curves in 2D space, also known as a time graph. Obviously, the standard workhorse to show temporal data. And great benefit, I don't have to explain how it works. There's a good reason to use workhorses, standard methods. One reason is that people are familiar with these. Yeah, you don't have to spend effort to understand how they have to be read. Another reason is simply that quite some of these are very, very good. Yeah, they survived. And the reason for that is that they can provide a lot of information in a very clear way. There's some interaction here in the real world version. Yeah, you could, for instance, click on a day in the year and then see the graph pop up. You could unfold all the patterns and see 365 patterns in parallel. You can play around with the measures used, the algorithms used for clustering. And driving all this is a simple form of machine learning, just bottom-up clustering. Okay, it looks a bit embarrassing to show such old stuff, but I'm happy to remark that 2 years ago I got the Test of Time Award for this picture. People still like it. Another example of visual analytics from someone Jan and I know very well, Paul van der Korpet, was one of the PhD students together with Jan in the project. Have you shown this, Jan, already in your multimedia?
So I have shown iClick, but I don't think this. No,
okay.
no.
This one is even more advanced. Okay, you have a big collection of images, and images have attributes. Now the challenge is what to do with these. You know, for instance, who made the picture, what is shown in the picture. This is where the machine learning and the intelligence come in to deduce that automatically. We have time and location. Now, given a big image collection, you can try to derive information. For instance, when were people active? When were certain concepts popular? What are the interests of people? And also you can reason about sets of people. Are the people that have the same interests were active at the same moment? This is his interface, and I would like to show it with a video. Now I have to do something risky and stop sharing, and then share my computer sound and find a video. Okay.
This video demonstrates the functionality of PictureVis, a tool for comparing personal image collections. Each image property has its own view: the person who made the image, the concepts in the image, the timestamp, the location, and the image itself. The glyphs show when images were made and by whom. Images are selected by selecting their properties. When a person is selected, the distribution of the corresponding images is highlighted in yellow in the other views: activity over time, interests, and the locations that were visited. Many of the images contain ships. Let's select them. Images without this concept have transparent glyphs. They are highlighted in yellow when they have the selected concept at the same time as the selected person does. This enables a quick comparison of the collections. Additionally, images made at the same location are marked with a plus sign. The characteristics of an area can be found by selecting the corresponding images and inspecting their distribution in the other views. The timeline shows an image burst here, so let's select the images in this time interval. The most relevant concepts indicate that there was a cycling event at the time. Images with the concept cycling clearly show the route of the stage. Visitors of the event can be found by sorting the people. Similarity and relevance are used to find interesting items given the current selection. With the concept train selected, the similarity column can be used to find correlated concepts. People can be sorted by relevance to find who has images that score high on this concept. When a person is selected, the similarity column shows who has a similar pattern. This similarity measure depends on the time window and a distance threshold that can be adjusted here. The glyphs show where the matches are. The images confirm that people are photographing the same object at the same time. Some people seem to be interested in this special train. Now we would like to find the people who have seen this train. This requires a custom concept, which is created by giving the system positive and negative examples. The new concept is automatically added to the concept view. We sort images by concept score and see that some refinement is still required. The similarity column shows that the new concept looks like a freight train and a locomotive. Finally, when people are sorted by relevance, we get the people who saw the special train. This concludes the demonstration of PictureVis. We showed how personal image collections can be compared and how to find the characteristics of people, concepts, time intervals and locations. Thanks for watching.
Okay, back to my slides. Good to hear Paul again, right?
Yeah, absolutely.
Okay, so far my short overview for the landscape. Are there questions so far?
So I believe there was one question in the chat from Sana, who asked with the calendar view, how did you cluster this data?
Oh, it was very straightforward. You have to have a metric to denote the distance between two day patterns. So I simply used Euclidean distance, or also offered other options, but Euclidean distance worked good enough. And then I applied bottom-up clustering. With this amount of numbers, well, it could be done very quickly, interactively, even 20 years ago on a PC.
Okay, thank you. So I have a question myself, but I'll let the students ask first. So if there are any questions, please feel free to unmute yourself and ask the question directly. And Sana says thanks. So there's a question by Asif who asks the cluster. I think cluster was done by pixel image or its metadata.
Both, actually, both. That was one of the driving topics in the project. You have the pixel data. From that, you derive concepts, but also you have this standard data that are recorded when you take a picture, like what camera was used. Hopefully you can also, by other means find out who made the data. I forgot what I think the original data we used was a Flickr database in this case, so you also knew who made the picture. In many cases, in visual analytics, it's about using heterogeneous data and trying to get things back. Yeah, very good question about the glyphs. Um, we spent a lot of effort in very carefully tuning the glyphs. If you just do something simple and obvious, it will be a disaster. So believe me that this was really an optimal choice. We used the yellow for highlighting the selections throughout. We use lightness to indicate relevance. I think also in combination with the size of the glyph, there was this aspect of not only time but also position. For that we used the plus on top of that. And of course, when you look at it at first sight, it looks quite intimidating and messy, but it works in the end quite well to see patterns. Especially columns, for instance, they pop up. You see here, for instance, a number of pluses below each other. You see an interesting row of similar things going on. So yeah, we think, yeah, on one hand it was simply a visualization challenge. How far can we go in showing everything in parallel? And I think it's doable. One of here's a little tip. One of the first things I always recommend to students to use is the format of a table. Yeah, and also here you see it's nothing but a table. There are persons here. There's time over there. Yeah, tables are excellent. You can sort the rows, and here we calculate the attributes and heavily use them to sort them again. Sort all the rows. Well, sorting things in time here doesn't make that much sense. By using tables, we rely on the fact that patterns pop up, like parts of rows and parts of columns, but also it facilitates scanning, linear scanning, which is very powerful. We can scan from left to right, we can scan up and down. So if you have to visualize something, consider using a table and use the ideas of the table in a creative way. Another strength of using tables is that on the top and bottom of the table, often you can also visualize aggregate information that can be very helpful. For instance, here you saw counts of number of items shown. That works well.
Okay, so thanks for the answer, and students, please feel free to ask further questions. I'm going to ask mine now, actually. So during your description of the work by one of the MSc students, you mentioned that you focused on pop-up free design, so that you wanted everything in the main visualization. So what's your general stance on pop-ups?
Avoid them. Yeah.
Avoid them. Okay.
This was one of those cases. By the way, in the demo you just saw, there was one cheat. We did not manage to get both the map and the temporal view in one picture. So you had to click on this icon or that to replace this by the map. But that is sort of an exception. The problem with changing views all the time is a short-term memory. As you probably know, in your short-term memory, there are only very few things that you can fit in. And once you show a pop-up, a lot of that is erased. Yeah.
Right.
And if you remove the pop-up again, okay, you have to remember what's in the pop-up and how does it relate to what's shown. So if you can get a stable display, things typically work much better. Something I tell in my own lecture and try to emphasize is that even if you look at a static picture like shown here, there's still a lot of interaction going on. And it's so natural that you almost don't realize it, but it's very fluent. It's focusing on something. Yeah, you will see something here, and you can scan what's going on here and find out, hey, there's a pattern over there. Yeah, and all this without having to touch something or enter some number or making a selection from a drop down or looking at a pop-up menu. Yeah, try to make your visualization such that you facilitate this very natural and powerful way of interaction, simply looking at stuff.
Right. Great design advice. Thank you very much for the answer. And we seem to have another question from Thijs. What kind of software was used to build the PictureVis application?
I think this was built using Qt and Java or C++. I even don't remember. This was at the time when D3 web-based stuff was not as ubiquitous as it's now. Yeah, I really liked that way of working. Qt gives a lot of flexibility and also a lot of built-in interaction concepts. So we were able to develop this kind of interfaces reasonably quickly, although there was a learning curve. Yeah.
Okay,
if you
cool. Yeah. Sorry.
No, okay. Now I'll follow my rant on development of technology.
No. Please continue. I just wanted to read that the student said thanks. That's so sorry. I interrupted you. I didn't mean to. Sorry, Jacob. Sorry. Please continue.
Yeah, one of the things I'm struggling with is that the technology, the programming languages, and the libraries and the tools change all the time. Yeah, so I struggle with how to teach my students, but also I struggle with keeping myself up to date. A lot of my own work I did in Delphi from Poland, Object Pascal, which provides an incredible, strong, powerful environment for very quick development of prototypes. Unfortunately, it has died out more or less. And well, I still have to make the step towards web-based development. These days, of course, using D3 is an obvious choice if you want to make some very fancy, powerful web-based visualizations. But yeah, the learning curve is quite steep, and I don't want to degenerate my lectures into a programming course, especially not only the D3 part, but also the web stack stuff. So yeah, I often leave it to the students themselves to choose whatever they want. These days, nice development is the combination of Plotly and Dash using Python. I've seen now quite some examples of students that are very quickly able to define some dashboards. But yeah, I'm not sure if something like this could be done. I guess it can be done. I don't know how difficult it would be to do it completely in Dash. As you saw, an interface like this was incredibly tuned. Someone like Paul could spend weeks to optimize it. Also, Stefan Elson was very, very good at tuning things until they were close to perfect. Of course, can be done with other technologies as well, but yeah. Okay, let's stop there.
Okay, fine. So let's take a break then, or what's your plan now?
Yeah, maybe it's a good idea to have a break and then have more stuff to tell.
Very good. So how much time would you like to take the break for?
15 minutes.
15 minutes. Okay, so we're gonna see each other at 10 again.
Yep.
Yes,
okay.
Perfect.
See you.
See you then. Reitze asked, with respect to design, do you have tools you recommend for collaboratively designing a visualization?
Collaboratively. Well, I'm a bit out of the practical part. So no, I don't have recommendations here. Ask your colleagues, they know better, I guess.
Yeah,
They manage, especially in these times of Corona, collaborative visualization of the web is getting more and more important. And well, I have teams of students working on stuff, and indeed, it's amazing how they manage to cooperate and develop stuff together.
Yes, and indeed we have Thijs to the rescue. He recommends Observable HQ, and yes, that I think that's actually a great suggestion. And I believe that's that Mike Bostock, the author of D3, is involved with that. So so I think it's a sort of like you have those what's it called in Python, Jupyter, I think, where you have these like notebooks, right? And Observable HQ does a similar thing, I believe. So that is a great recommendation, Thijs. Thank you. But okay, we're going to start. I'm going to give the floor to Jack again to continue with the lecture.
Okay, I finished here, and of course, when you try to get rid of information, there's always a risk that you lose something. And the question is, should we trust the results? No. Should we let the computer decide on that? It's a big question, and there's a lot of discussion around it. If you want to read a lot of horror stories, then I strongly recommend this book from Casey O'Neill, Weapons of Mass Destruction. It's already a couple of years old, but I fear that things have gone worse. When I first read this book, I thought, yeah, okay, very bad things are happening. But yeah, this is the US, yeah. I hope that in Europe and in the Netherlands, we try to avoid very bad things. But unfortunately, that's not completely true. Here are some messages I picked up from the news. Dutch government uses predictive algorithms on a big scale, and there's a risk for discrimination. This is an intriguing message. Siri, the fraud detection system of the Dutch government fails. Not a single fraud case was found. Okay, so far for the power of AI. And also there's a risk of discrimination. People that live in poor neighborhoods are suspects in advance. So it is important to get transparency in automated decision making. And these days, this, for instance, also enforced by the GDPR. Let's get a picture of what's going on. We have to present the evidence and reasoning such that people can judge, understand, validate what decisions are made. Responsible data science is getting a lot of traction. Here is a logo that I made for a big project. Unfortunately, it was not granted, but you see that transparency is a key point in responsible data science. And also we have had quite some activities in this area. These days it switched a bit to explainable AI, XAI as the main buzzword. And you see that there's a lot of attention in that, not only in the hardcore machine learning, data mining, AI communities, but also at HCI conferences, and especially also in visualization conferences. Quite some papers are presented on people trying to work on this and improve on this. Okay, what is the problem at stake? We have very complex models making decisions. Here is a list of number of standard models with increasing complexity, starting with simply rule-based decision-making via regression decision trees up to deep learning networks with millions and millions of free parameters. It's not only the type of the model, scale also is an important element here. If you have 1,000 rules, no way that you can oversee them and reason about them and understand what's going on, or at least it's very hard. Now, who's at stake? First, you have the subject decided upon, you have some decision maker, you have some data scientists, the data scientists making a model. Well, you know probably how to make models. Next, the model is transferred to the decision maker who applies it to cases of a subject, gets a labeled case, and based on that, he has to make a decision. This is roughly a sort of standard pattern. You see that in this case, there's a human in the loop. In other cases, things are even more automated. Now, there are a lot of questions you can ask here. Looking at a subject, do I understand and agree what's decided on? Decision maker has to check if the label that's given matches with his own domain knowledge. Typical example here is that if someone is getting a fine because the color of his hair is red, okay, he must be suspicious. Also, the data scientists must make sure that his model is correct. Not only that it achieves a high accuracy, but also, for instance, that the parameters, features that are used make sense. Big problem, big puzzle with many questions attached. You see that the stakeholders have very different needs and capabilities. Presentation as such is a big challenge. And also with respect to interaction, you want to enable people to drill down what's going on and enable them to answer the questions they have. So there are roughly 2 dimensions in this playing field. The first one is that you have to make a decision on how you approach the model. You can try to show in detail what the model itself is doing up to the level of the mathematics used, white box model. Another approach is to simply consider your black box model as a black box, as an oracle that spits out something, and use some simplified model to explain what's going on. Another dimension is the scope. On one hand, you can try to show for all possible cases what will happen. In other cases, it's a better idea to focus just on 1 or 2 selected cases and try to get a good explanation for that, which is often already hard enough. Okay, the questions, meanwhile?
So yeah, we had a question from Raitse, which was a way back about I think it was related to the automatic decision making that where you kind of asked this question, like, would you want this for your career? There's almost more like question / remark, but Raitse, that's Amazon's Mechanical Turk, basically, right? So that's what he remarks. That interesting career choice of labeling images ad nauseum.
Yeah. That's a good point, indeed. In the real world, people are doing that, but yeah, it can earn you something, but I don't think that working for Mechanical Turk is a sustainable career, so to speak.
Indeed so, indeed so. We also a question by Gian. For online tools, it is difficult to show a white box. Is it therefore even an option for online tools?
Yeah, in all those questions, it's very important what the size or the scale of the model is. For simple cases, I think you can show it. Yeah, and for instance, Google has a number of very nice demo sites where you can play around with very, very simple models developed by Martin Wattenberg, one of the strongest InfoVis people I know. Yeah, if you go much further, it's getting difficult. It's also a big question who you want to allow to look at it. Of course, if you are talking about things like fraud detection, the company doesn't want to show all the rules they use to avoid that people will game the system.
Yeah. Okay, thank you. There's a question from Ahmed. As per your conversation regarding bad machine learning models, is there a framework we have to check to make sure the ML model is the right direction away from bad consequences?
As far as I know, no. And this is actually one of the maybe the big challenge here. Yeah, how can you check that the model is okay? And there are many aspects in these questions. One is technical, just showing things and calculating things and stuff like that we're talking about here. But also there are a lot of legal and ethical aspects. I've been active in preparation of a big project, working together with people with a background from law. And one thing I learned from them was that they do not focus that much on the details. They focus a lot on the procedures. Yeah, for instance, that you have the right to have a second opinion or the right to get insight into this and this information. And important part here of solving this is to learn from those.
Okay, thank you. And if you permit me to append the technical perspective from machine learning to this answer. So there are what machine learning practitioners generally use is called adversarial examples. So those are typically, especially in the domain of images, those are examples that I mean, it's for example a panda. And you would expect it to be a human instantly recognizes that image as a panda, and but a deep net will classify it as a freight truck, for instance, for some reason, because of some mathematical distortion. So there's a set of these adversarial examples that you can run through your deep net, for instance, and see how you score on that. There are also, I believe, example sets to kind of internal, because you don't want to share this, exactly to combat racism, for instance, and these sensitive topics. So this is from the technical perspective. This is just an addendum to Jack's answer, if I may.
No, you're perfectly right indeed. Also, your examples show that it's still a tough question.
Yes.
The adversarial examples, I find them incredibly fascinating and intriguing, but yeah, they're sort of point samples. And if you want to make a statement, my model is okay, yeah, you have to scan a lot of the space and to check out many things.
No, yeah, that's a very good point, because if your model runs these adversarial examples and classifies them correctly, it still doesn't mean that you can have a blanket statement that your model is all right. It's just that you know that you haven't failed on these examples. So basically, they just give you a quick failure, but they don't give you the general statement that your model is right. Indeed.
Yeah, and then yeah, if you work in high-dimensional data, yeah, high-dimensional space is so incredibly huge. So another remark is that if you take, for instance, discrimination, one intriguing thing I heard about, I'm not an expert in this, but you can define discrimination in different ways, and you can prove mathematically that it's not possible to find a method such that you satisfy all the constraints given by different approaches to defining discrimination. So you have to make a choice first. I define discrimination as this and this rather than such and so, and then you can try to work on that, but it's not possible to find a method that will satisfy everything.
Yes.
So.
Okay, thank you for this answer. And we have a question from Martin. With the errors shown in automation, like the traffic light or the tax office fraud detections, is it fair to blame automation when people design and build these systems? You generally never hear from automation/engineers when stuff does work fine, because that's the point, right?
I fully agree. It's all work of humans, and in the end of the day, it's a human responsibility. Yeah. As a very different example, think about crashes of planes. In the end of the day, it's always a human mistake. Yeah, and a similar thing happens here. Meanwhile, how to deal with that and how to check and procedures to fight it, to detect it, well, still a lot of work to be done. I think that everybody has an important role in this, especially, for instance, journalists, but also members from parliament, etc., etc. We recently had the kindertoeslag disaster in the Netherlands. And also there was one of the ingredients was discrimination, dependent on your background, migration background, you got higher on the list of being checked. Yeah, so it really is important to check this out continuously. In this kindertoeslag case, it was a frightening example that it takes a long time before people get aware, and even much longer time before people take their responsibilities there.
Right.
I had a question on discrimination, if I may.
Yeah, sure.
Why is it mathematically interesting that you cannot define a sort of function where you do not discriminate? Or because like a model is supposed to discriminate anyway, right? It's supposed to discriminate on certain factors, and we as a society don't like to discriminate on certain things, and we want to prevent that. So that's built in, right? So we're always going to discriminate on something, right? You cannot make a model that doesn't discriminate on anything.
No, but you can try. Yeah, you can try.
What can you try exactly?
Not to discriminate. Yeah, you can try to make sure that people are treated the same, independent of their, say, migration background or gender or whatever. But if you can show that you can define that in different ways and they are mutual conflicting, well, that raises awareness that you have to be very, very carefully in how you define discrimination. And maybe it's unavoidable, but still it is important to take it into account and try to make sure that you're doing as well as possible.
Yeah, obviously it is. I think it's just because the way I see discrimination, there's different definitions, right? So there's a sort of ethical and legal definition, and there's just discriminating also in math, where you're just making a difference between things. But I understand that, of course, I think I understand what you mean. Yes.
Okay.
Okay.
Okay, one last question, if we may. So we have again from Gian. With nowadays technology / possibilities, which visualizations from your career would you like to redo? Which ones do you think you can improve now?
Well, if I look at things that I did 20 years ago, take for instance the cluster calendar plot, I now see that the colors could have been chosen better and I should have used thicker lines. But yeah, that's just growth in insight and experience. And I don't think that the technological part compared to 20 years ago makes that big a difference. Maybe you can calculate more, graphics is faster, but yeah, the overall design and design of the interaction still remains the most important thing. And I definitely, for now, don't believe that things like VR will open up an incredible lot of new opportunities.
Okay, thank you.
Okay, I would like to show some examples of stuff we did in this direction. First, decision tree visualization. The idea was, okay, let's try to make a tool that enables domain experts to steer the derivation of decision trees. It's a typical example of a white box approach, where the model is shown explicitly and also where you show all the cases in parallel. This was master thesis work from Stefan de Elze. Well, you see a fairly complex dashboard with a lot of different features. Here you see the decision tree itself. In this case, there were about 8 different classes indicated by color. And here the colored bands represent where certain cases are flowing through. You see that it's difficult to split blue and orange at this stage, but using a different feature, suddenly it's easy to split things. This was a particularly nice feature. You select one node and here you get a list of possible features that can be used, sorting for their effectiveness. So this is where the domain expert comes in. He can look at the labels of the features and try to judge if they make sense or not. There are some standard visualizations here, confusion matrix for the test data and the train data. There's a navigation window. This is zoomed in version of a larger tree. Here you see the raw data, and also here you see a lot of buttons that you can use to manipulate the visual representation shown here. And by playing around with that, you could make pictures like this, where the nodes themselves are a bit hidden and things are shown more like a flow diagram. Same spirit here. Well, he got a nice paper out of this. Also interest from the outside world. Several people asked if they could use his tool. Well, each time we gave it away, we never heard back. And when we inquired, we always got the same reply. This tool is limited to decision trees, and in the real world, random forests are much more effective and hence also much more popular. Unfortunately, random forests are much more difficult to visualize. Yeah. Big benefit of a decision tree is the fact that it's easy to visualize. Yeah, there's a very natural mapping from the models to some graphical model. That makes it possible to understand things. That makes it often a good choice if you want to have some simplified model. This is a case from a medical application, polysomnography. Suppose that you have some sleeping disorder and it's serious, and you're taken to a special clinic. They put a lot of sensors on your brain and let you sleep over the night. Next step is to analyze the signal of the sensors. And typically what they do is they chop up the data into intervals of half a minute, and each of them are classified as being one of the 5 sleeping stages, running from being awake up to REM sleep with some stages in between. This is hard, yeah. If you are an expert, it takes about 1 hour to do this classification. You could imagine, let's throw in some fancy AI and automate this, but also there you find out it's quite hard. The accuracy that's obtained is typically 85%. Umberto has explained me how people classify things and what features to watch out. Then I understood why it takes so long. The features you have to look for are incredibly subtle and hard to spot. You really have to be an expert, and then still, yeah, there's variation in the results even among the experts themselves. Now, it seems obvious to combine things, and Umberto made a nice tool to support that. Tool consists again of a lot of different views. You can have a view of the patients. Here you see a histogram showing the distribution of the different stages. Here you see the stages overnight. He used, I think it was a TSNE plot to visualize the different half a minute intervals. Intervals that are close to each other are put closely on the screen. This is another view of the intervals. Here now a simple block pattern, enabling to see patterns in parallel. And if you're interested in one particular case, you can click on it, and here you see detail on what's going on. And the background gives a cue which features were taken into account. The lighter the background, the more important that particular feature was. This is what the integrated system looked like. There's also a confusion matrix shown here, different projections, and well, it gives a lot of opportunities to drill down onto the results of the predictions and overrule them where needed. A different case, this is typically using a white box, strongly simplified model, and for only one particular case was a project we did in cooperation with the University of Nijmegen and also Thales. Thales is a company mostly known for making radar systems, but also they make control rooms for coast guards, for the military, to scan what's happening on the sea. This is schematically the use case we studied. There's a lot of observations. These are put into a reasoner, and the reasoner spits out something like one particular case is dangerous, and also gives some judgment how dangerous it is. In this particular case, it was about ship data, AIS data. AIS is a sort of GPS device that sends out the position of a ship, originally developed to prevent ships from crashing with each other. But also there's radar data, web data, even tweets, Facebook posts, databases, all about vessels. The reasoner in this case was a probabilistic first-order logic inference engine. Very, very sophisticated, very, very complex. Think about of huge matrices, size 500 times 500 that are completely filled. And the decision maker here is a ghost card. Yep. Now, think about it. The ghost card has to make a decision like, okay, let's send an inspection ship to a suspicious ship, or send a helicopter because someone is having problems at sea. But if you only get a signal 75% dangerous, yeah, you want to have a bit more background in the decision. Fortunately, our colleague from Nijmegen, PhD student Stephanie Michels, was able to derive a very simplified picture from what the reasoner was doing for one particular case. And our PhD student, Roland Schepens, worked hard on making a simplified presentation. Here you see what it looks like. Here you see the conclusion, increased chance that the ship is reckless. And why? Yeah, because it might be smuggling. Why do we think it's smuggling? It's hiding its identity. Why does it hide its identity? Well, it's messing around with the AIS device. That's a sort of fake ID put in, and that's quite suspicious. There's also counter evidence, like for instance, in the past there were no collisions known, etc. Here you see a schematic overview of the raw evidence. In this case, each column represents one source of evidence and each row a feature. Take, for instance, the name of the ship. You can click on this, then get information. 5 of them think the name was Blue Pearl, 2 think it was the Flying Dutchman, and 1 think it was something else. One cool trick, quite subtle, was choosing the colors. The colors are choosing here in such a way that if there's agreement, the same color is assigned. And now you see that there's one group of sources that thinks one way, another group thinks into another way. Maybe there is confusion about the identity of the ship. I could explain it. Okay, another case, fraud detection, was the master project of Dennis Colares. After this project, fortunately, he stayed in our group as a PhD student in the same area. The aim here was to support a fraud detection team at an insurance company, Achmea, in prioritization of their cases. Yeah. And again, use a very strongly simplified model, just one particular case. The starting point were a lot of insurance policies with about 50 attributes per policy, and there were 129 cases that were confirmed fraud. Yeah, at that time we were not that experienced yet. This should be quite alarming. The data set is highly unbalanced, as you see. The company has developed a machine learning model trying to make sense of these data. It was very, very complex. You probably all know random forest. Well, this was the next level. Collection of 100 different random forest models, where each independent model consists of a lot of decision trees. Somewhere halfway his project, he made a TSNE plot of the data, and this was truly frightening. You see that the red fraud cases are scattered all over the space. There's not too much similarity there. Meanwhile, Dennis did his best to make sense of the data. Here you see different sort of standard ways to visualize things. You see, given a certain feature, what happens with the probability of being fraught when the value is changed. Oh, no, sorry, this is slightly different. It shows for given a certain value of a feature in general, what's the chance that something, how important is that feature for making the decision? This is the case where you look at one particular case and what will happen if we vary the value of a certain feature, so-called dependence plot. You see that in most cases, the effect is not that strong. He used a method to automatically derive sort of rules and used it to make this decision tree style diagram. We learned a lot from this case. We found out that it's very hard to find clear-cut explanations. Probably in this case, the model itself was simply too complex and there was not that much structure in it. We also found that if we threw different techniques on it, you got different explanations, different features bubbled up. And some weird thing we noticed was that when we showed it to the domain experts, well, they seemed to be happy with everything that was shown and did not seem to care that much about this variation in the explanations. Dennis has continued work on this, and one of the results is this system, explore. If you want to look more about it and even play around with it yourself, go to his website, explaining.ml. There you can find the paper, a video, and an interactive demo. Dennis is one of those new generation students who's a total wizard using D3, JavaScript, Python, and all this stuff. Roughly what's going on here is that you see a parallel coordinate plot. One mode is to show the parallel coordinate plot for the data, but you can also visualize it using feature importance. And that gives you an interesting information what features are taken into account. Are there different clusters in there? Here you see a zoomed in view on one particular case. You have one focal point here, particular case, and a small environment around it is also shown. And here some neighboring cases are highlighted. And of course, this is totally interactive. You can move those points around and scan the space and decide what you want to see, etc., etc. Okay, well, this concludes my lecture. I've told you something about InfoVis visual analytics. Probably you already know a lot about it, thanks to all things that Jan has told you. I hope to convince you that transparency is very important. It's still a really difficult and very challenging problem because of the size of the data, complexity, and even it's hard to define what you really mean by transparency. Good news, of course, is that there's plenty of research that can be done. Now it's time for my final takeaway message. Next time you see a red light, it's a good idea to stop for it because you pay a high fine. Thanks.
So thank you, Jak, for your wonderful lecture and for joining us here today. Do we still have time for a couple of questions if the students have them?
Sure.
Yeah, so last chance of asking Jak about visualization. So use this opportunity. In the meantime, while you think of your questions, I have two of them myself. So with Roland's system about the decisions about the ships, what is the time from receiving the data to the actual decision? Because I'd imagine it's we have this AIS data flowing in, right?
Yeah.
And you need to make a decision rather fast. So what's the pipeline, the time to decision time roughly?
Yeah, to be honest, I'm not sure. I also, yeah, I don't know the current status of the affairs. This was in cooperation with the Embedded System Institute, at that time part of our university, that has moved to TNO.
Mm-hmm.
And I think they're still working on this area. I don't know the adoption of this kind of methods.
Mm-hmm.
Just thinking aloud, I think this is a continuing process. Yeah, you receive a first message that something might be wrong, next messages. Yeah, the time to decide, I guess it will be hours in cases. Yeah, it also gives you some time to do additional checks. Of course, there are extreme cases when people are drowning, etc., when you have to try to react as quickly as possible.
Okay.
Okay.
Thanks for the answer. We have a question from Gian. Where do you think InfoVis as a discipline will move to in the future, and what new challenges the field will encounter?
Well, I think explainable AI will continue to be a huge challenge. Yeah, I think that automatic generation of visualizations also will continue to be an important challenge. That's in some sense already an old field. In '86, Jock McKinley made his PhD on automating choices for visualizations. And quite some people have worked on that. And of course, it's not solved at all. There are reasons why automatically generating visualization is a good idea. One of them is that, well, it helps people and they don't have to spend time on thinking about what's the best visualization. There's also more intrinsic reason for that. Once you can automate designing visualizations, that means that you have fully understand how to do that. On the other hand, yeah, Jan and I was just discussing that. In the end of the day, there always will be a very strong design component, because as a user, as a spectator, you have to decide what's important, what's not important. And that's some element that is very hard to automate. Yeah, I still hope that new, very powerful ways to present the data and to interact with the data will be found. On the other hand, one thing I often tell my students, it's often hard to beat the trivial solutions. Yeah? Take a line graph for showing temporal data. Well, in many cases, that's superior. And each attempt to make it better fails. So in the hardcore presentation part, I don't see big things coming, but I hope I'm wrong. Meanwhile, interaction is important, and careful attention to that really pays off. Enable people to specify what they are interested in, what they want to see, to ask questions just by clicking on something and without any effort. And well, in well-designed interfaces, you see that's happening.
Mm-hmm. Thank you for your answer. So I'm gonna ask one minor question myself. So please, if you have questions, still write them in the chat. Ask away. So on slide 72, you mentioned violin plots. Is that a stream graph?
Wow. No, it shows the horizontal axis is the value for one variable, and this shows the distribution over that variable.
Okay.
It's just like a histogram, but mirror symmetric, and well, looks cute, doesn't it?
Yeah, it does. It does. Absolutely. It's just a violin plot. It was a new term to me, so I wondered what the definition is. Thank you very much. And we have one more question from Raitse. What is your general opinion of TSNE as a visualization?
Yeah, I'm a fan of TSNE, and especially if you want to see clusters in the data, it can be very powerful. Meanwhile, by definition, if you start to project data to 2D, you lose information. Should always be aware of that. TSNE, like many other algorithms, has parameters, and the way you set the parameters influences the result. There's, again, from Martin Waterberg, nowadays at Google, a wonderful website enabling you to play around with the parameters of TSNE and see the effect. I understood from my PhD students that currently another projection method is getting increasingly popular. I forgot the name. UMAP, exactly. One of the big advantages is that it's much faster than TSNE. Yeah, and yeah, the longer you're in the field, the more cynical you get. It is tempting to look at complex visualizations, including TSNE, and try to find all kinds of little subtle things. Well, I warn my students, don't go into the business of judging tea leaves. Yeah. If there is a strong effect somewhere, it should be visible, right? And visible without having to carefully tune the parameters or zoom in a lot or playing around with your visualization. No, if there's really a strong distinction between two groups of items, for instance, you hope to see that immediately. And in many cases, it can be just the result of some random noise. Concerning challenges in visualization, that's another important one. As humans, we are very good at spotting patterns, but the downside is that we tend to see patterns everywhere. Yeah? And using methods like TSNE, but also almost any other method, there's always a big danger that you are just looking at noise. So, yeah, I think it's an interesting challenge to make that clear in your visualization itself. Yeah, okay. Is this significant? Does it make sense? Is this real data? Is it real pattern we are looking at, or is this just random?
Okay, thanks. So I think we can conclude the session. So again, Jak, thank you very much for taking the time to be with us here today. And yeah, I think we all enjoyed the lecture. And thank you, students, for coming. And we're going to see each other tomorrow with Stevan Rudinac's guest lecture on multimedia analytics for urban computing. Thank you very much.
Bye.
And bye-bye. And Jak, you mentioned